Okay. The next point, next content is troposphere and ionosphere, scintillation and low angle fading. What is the meaning of this troposphere and ionosphere? Is nothing but what? Where we are living, that is the layer of troposphere, and which is more, the distance is more than that of the Earth atmosphere, that is of ionosphere. And scintillation is the flash of light, sound, and waves. That is called a scintillation. And there is a different angle of fading in the waves, that is called as low angle fading. What is ionosphere? The ionosphere, which is a little bit more than that of the Earth atmosphere. The distance is more than that of the Earth atmosphere, that is ionosphere. And the troposphere is where we are living, the Earth station, that is called as troposphere. And the scintillation is, that is a flash, that is a uh, flash in the light or sound or the waves, that is called as the scintillation. And in this troposphere, and this troposphere where we are living, that is divided into different parts. That is, one is the rain and the snow, the scintillation, that is wet or dry, that is, one is clouds, and the next is oxygen absorption, and one is water vapor. These are the different categories or the parts present in a particular troposphere. We are observing the rain and the snow, and we are observing the lights, that is at the time of rain, that is scintillation. And the clouds, we are observing the clouds, and oxygen absorption is there, and water vapor, that is also important for the troposphere. What is there? The ionosphere is nothing but the layer of Earth atmosphere which contains a high concentration of ions, and free electrons, and is able to reflect radios. Whatever the radios for the different types of signals we are using, it is going to reflect from the different concentration of ions and electrons. And whatever the height of this, what is the height of this ionosphere, is more than about 82,000 kilometers from the Earth atmosphere. And the troposphere is where we live. Troposphere is where we live, that is the lowest region of the atmosphere, extending from Earth's surface to the height about 6 to 10 kilometers, which is nearer to our Earth atmosphere, that is called as your troposphere. Okay. The ionosphere is a region of ionized plasma that extends from about 50 kilometers to 2000 kilometers towards the sky. It is nearer to the sky, and that is to be distance nearer to the space. A small percentage of molecules are ionized. The majority still remain neutrally charged. That is, the charged particles, that is holes and electrons, are remaining. The majority particles has to be charged. This layer highly impacts RF communication, that is radio frequency communications of wavelengths below microwave signals. That is my below microwave up to the about 10 gigahertz. So our topic at hand, it is of low importance, but listed some of the factors affecting radio frequencies. The frequency is above 10 gigahertz in this range. That is to be, we have to follow some of the parameters. Those parameters are nothing but what? One is critical frequency, and second is total electron content, and Faraday's rotation, and fourth is group delay, and fifth is phase advance. That is, the next is Doppler's frequency, and last is dispersion. What is the frequency we are using in this particular? That is critical frequency we are using in the troposphere. And the total electrons present in a particular atmosphere, that is also important. And a delay of particular particles, the delay of particular particles, electrons, holes, and ionized particles. And the phase advance, that is, you have to calculate the psi. And Doppler shift you have seen, that is Doppler frequency. That is, Doppler shift frequency is also important, and dispersion of waves, that is also important in the ionosphere, because this ionosphere is a distance more than that of the troposphere, that is to be present at the near about the sky. And also ionosphere scintillation, which is a relatively rapid fluctuation of the signal. Rapid fluctuation of the signal about a mean level, that is either constant or changing much more slowly than the scintillation themselves is a major phenomenon that affects the integrity of radio signal. And this signals are going to affect a particular troposphere, and it is to be rapid fluctuation of the particular signal. It is going to have a higher energies. When this ion energy can be converted to the another form of energy, the fluctuation of the signal will going to affects based on this radius of the signal. And previously we have seen the gaseous absorptions, atmospheric absorption, a different types of atmospheric absorption. One is ozone, one is water vapor, one is carbon dioxide. These are called as gaseous absorption. Similarly, as mentioned here, the different types of gaseous absorption, that is ozone, that is O2, and that is your H2O, that is water vapor. This atmospheric attenuation due to gaseous absorption is dependent on frequency, that is absolutely right, that is frequency, elevation angle, the angle of antenna LOS versus horizon, and the altitude of the station, the total path to the atmosphere, which is a function of theta, and we are going to calculate the particular low angle fading. The low angle fading of particular signal should be in the horizontal. That is the elevation angle we are going to calculate with respect to the theta. With respect to the theta angle, we are going to calculate the particular antenna present in a particular satellite. That is a distance with respect to the height, that is h. Okay. When absorbed, the radio frequency energy is converted into the heat. Whatever the energy is to be converted, it has to be converted into the heat in the form of energy, and is a prime culprit when it comes to the gaseous absorption, attenuation of any SATCOM signals. So whatever the signals is going to affect a particular ionosphere and to the troposphere, it is to be converted into particular high energy into the low energy of the signal. So it is to be protected from the human beings. Oxygen is a paramagnetic molecule with a permanent magnetic moment, which leads to it having resonant absorption at a particular frequency. You have to have a particular frequency to convert a higher energy into the another form of energy. If you want to have a frequency that is to be more than 10 gigahertz of frequency, there is a getting the more fluctuation in the signal. So for water and water vapor, being a polar molecules, also leads to a resonant absorption at a critical frequencies. You have seen in the previous diagram, there is a frequencies we are using. Based on that, we are using the three absorptions of gaseous absorption, the water vapor, one is carbon dioxide and one is ozone. Based on that, it is going to have a different types of gaseous absorption. We are using the frequency of 22.3 gigahertz, 60 gigahertz is due to oxygen absorption. The oxygen absorption, which is mainly present in the ozone, that is ozone is a frequency range is of 22.3 gigahertz to 60 gigahertz is the oxygen absorption. As for the rest of the gases in the atmosphere, it is not until the higher frequencies greater than 70 gigahertz at their absorption comes significantly towards the attenuation of the signal, where the signal is going to attenuated the mainly at the maximum is of 70 gigahertz, because ionosphere is height is of 82,000 kilometer, or from the 1,000 to 2,000 kilometers. So frequencies goes on increases. As the frequencies increases, so the signal fading is also get diverted. It is also get reduced. So this is very important for the ionosphere and troposphere of the particular signal. And the next is scintillation. Scintillation is nothing but that is a flash of signal. If there is a flash of signal is going to happen, that is to be changes in the amplitude, altitude, and refractive index of the particular signal. Scintillation is nothing but they are in the general variations of received signal level amplitude or phase caused by the refractive index variation of the troposphere or the ionosphere. It may be the scintillation may occur in the troposphere or in the ionosphere condition. At any condition, at any layer, it is going to happen. It is going to calculate a particular refractive index of a particular signal, received signal, and it is to be calculated based on the variation in the amplitude of the signal and based on the altitude of the particular signal. When the propagation path atmosphere is not turbulent, the refractive index varies very slowly in the horizontal plane and a bit faster with the height. When the path of the particular propagation is nothing but the radiation of light, that is propagates a particular light sound on the waves. If there is a height and the distance goes on increases, we are going to get the variation in the refractive index. It is not a constant. Refractive index is not a constant. There is, you have to observe a particular variation in the particular refractive index as the height of this goes on increasing. That is nothing but your path. But due to the fact of wind, the path becomes a mixture and causes relative rapid variation in the refractive indexes for a small amount of time, which we pursue as a scintillation. If there is a variation in the refractive index goes on increases, this meaning is that there is a scintillation in the signal, there is a variation in the signal, there is a flash in the particular light, and it is going to have a low angle fading. That is to be low angle fading is nothing but that is a refractive index goes on decreases. The major factors is giving the greatest scintillation amplitudes are a high temperature and the humidity leading to strong seasonal dependence. The summer scintillations are above 3 times as severe as winter scintillation. When they are observing the particular scintillation, it is more at the time of summer as compared to the winter scintillation. They are saying this. And next is your rain and slope. Rain is a main degradation factors affecting different types of satellite communication operating at frequencies above C band. When there is a rain is going to happen a particular frequency band, if the C band is 6/4 frequency band, if it is more than that, if you are having a 14/12, if it is 14/12, that is of KU band, and 24/20 is your Ka band. If it is more than that, it is going to have a particular frequency in the signal, that is C band. Raindrops both absorbs and to some extent scatters the RF microwave energy. Dry areas and the seasons with low rainfall requires a less link margin in contrast to the rainy, heavy thunderstorm season with a low rainfall requires thunderstorm activity location. Where this is it is going to happen particular dry areas at the time of raining, and we are going to happen particular thunderstorm activity of the particular locations. Rain also introduce depolarization. This is due to the non-spherical shape of raindrops. The depolarization of particular signal is observed because of shape of rainfalls. The raindrops are not particularly the same as compared to the different types of the signal. And the snow attenuation only starts to be concerned at the frequencies higher than 100 gigahertz. Thus it can be neglected. Whenever the snow attenuation of the signal is going to affect, the frequency band is more than 100 gigahertz PSI. Rain attenuation has been extensively studied since some of the potential service subscribers would experience rain as both a passing event, or they might be located in a heavily rain affected region. So it is going to have a particular frequency band is of more than 100 gigahertz. If the variation of the frequency is near about 20, 40 and 50 gigahertz, we are going to have a particular signal variation in the signal. This is what the troposphere and ionosphere of the particular signal. The main important thing is what? In the troposphere, how much is the angle going to a particular angle should be attenuated, and in the ionosphere, how much is the angle fading is going to happen in the particular signal. That is very important. Based on that, they are going to have a particular frequency band of that signal, and based on that frequency band they are going to have a particular decision making of the system, that we are going to have which frequency band we are going to consider, that is to be considered main most of that the particular signal. And the next is rain induced attenuation. You have seen in the previously the difference between the rain and the cloud. The cloud is more important than the rain. The rain attenuation is a major challenge to microwave satellite communication. Whenever your signal is going from our station to the particular satellite, we require a particular microwave signals, microwave frequencies, especially at a frequency about 10 gigahertz, causing unavailability of signals most of the time. When the signal is, when the particular microwave frequencies is having more than 10 gigahertz, that is to be causes a particular induced in the signal, that is diverted in the signal, that is to be frequency band is of 10 gigahertz. Rain attenuation prediction. Rain attenuation prediction has become one of the vital considerations while setting up a satellite communication link. When we are going to have a particular rain attenuation, okay, when you are going to have a particular satellite link, there are two links, one is uplink and the one is downlink. If you want to calculate a particular rain attenuation in these two links, that is one is uplink and one is downlink, we are going to have a particular consideration of the particular prediction of the signal, or depending on the uplink and the downlink. Rainfall is a major cause of signal degradation for a radio communication system. So rainfall is a major degradation, signal degradation. When there is a rain, we are not accessing the signal, but 5 to 10% we are going to access. If there is a heavy rain, there is a loss in the signal. That is a signal degradation in the for radio communication systems operating at a centimeter or millimeter wave bands. When there is a rain, the particular frequency band is going to reduce from the centimeter to the millimeter of the frequency wave. That is a band, especially in the tropical region environment. Rain attenuation of satellite signals do not simply affect the end users resulting performance, it is also affect the cost. Whenever they are launching the satellite, and that satellite has to be reached to the particular space, if we, whenever they are launching the satellite, they have to do the finalize the particular budget of the particular satellite, and at the time of different seasons how much is the signal we are getting, they have to be predicted before designing any of the satellite. At the time of rainy, at the time of winter, we are going to loss in the services of the particular satellite, so there is the degradation, there is a loss of the particular cost in the particular of the satellite signals. Rain attenuation causes a greater power requirements. It requires a more power requirement for the particular subsystems present in a particular satellite from the transmitting units, which hence leads to a higher cost per bit of transmission. Whenever the signal is transmitted from the Earth station to the satellite, and the satellite is having this a number of substations. In those substations, we require the most important quantities of the power subsystems. Power is mostly requirement is the 100% requirement is of power, and this power is given to all the subsystems present in a particular satellite. Okay, if there is no power, the satellite can't work. So power is the most important subsystem present in the particular satellite. While they are going to manufacture particular satellite, they are going to have a power subsystem with a maximum cost for the transmission of signal and for the conversion of signal into another form of signal that is required. And power is most important thing. So they are going to install a particular batteries and particular solar panels with the most power important power factors present in particular satellite. The consequences of this rain attenuation are as follows. What is the, if there is a rain attenuation is there, what is the effects we are going to observe in this? The loss of signal strength at the receiver. The first is what? If there is a rain, we are going to attenuate the signal. That attenuation is nothing but loss of the signal. Okay, we are not accessing the particular signal at the earth station if there is a rain, so loss of the signal at the receiver end, the particularly your TV cable. Wastage of transmission power in a bid to overcome this form of attenuation. The transmission power is also waste at the time of rain. If you are receiving the signal, the still the power is present. That is a wastage of signal. The power is unable to receive the particular signal, so there is attenuation of the rain. Attenuation will be takes place. Next is total loss of signal at the receiver in the extreme cases. In the most of the cases, the extreme cases, you are going to observe the losses of the signal. You are not able to get that particular signal at there is a, if there is a cloud, if there is a rain, there is a extreme losses. There is your they are going to calculate a particular losses present in a particular earth station. That is a total losses they are going to calculate. Unavailability of the satellite link for a great percentage of the time. A link, it is very important for getting the percentage of the particular signal. So uplink is there and the downlink is there, and two links we are going to have in the particular system. How much is the percentage we were getting at the time of uplink of the signal, and how much is the percentage we are getting at the time of downlink of the signal? And that is very important for this, the get great percentage of the signal time. So these are the two contents we have to see today. So only four contents are present in this topic. And this in number 5, one is atmospheric absorption, cloud attenuation, tropospheric and ionospheric scintillation and low angle fading. And last is your rain induced attenuation. This is a new unit he has mentioned in the last year. So we have seen in the atmospheric absorption first, and next we have seen cloud attenuation, and next we have seen the tropospheric and ionospheric scintillation and low angle fading, and next is your rain induced attenuation. Thank you. This completes your unit number 5. Okay, we'll start with the remaining part of tutorial. Okay, anyone is ready? Those who are not given, please. No one has prepared?